This is Module 10, first video. We're going to think a bit about correlation versus causation. We're going to do this just kind of logically, and then we'll get into the details and new vocabulary terms in the next video. So, in general, if we see a pattern that exists between an input and an output variable, what could we say about the cause of that pattern in the data? Could we conclude that the output variable is being caused by the changes in the input variable? So I just have a few silly examples here for us to just kind of think about all this logically. So this is a famous graph that comes from the open letter to the Kansas School Board, which is a funny letter if you ever want to read it. It says along the horizontal axis, number of pirates. You'll notice that the axis values are going backwards, and one of them is labeled weird. And anyway, it's just a funny, silly graph. But in general, it seems that it's saying that as the number of pirates goes down, the global average temperature is going up. And it seems to imply as if, as we have less and less pirates, that's causing the global temperature to go up. I mean, is that a conclusion you could make from a graph like this? Can we really conclude that the global average temperature changes are being caused by the number of pirates in existence? As a second example, here's another silly graph. Along the horizontal axis, we have the years spanning from 1997 up to 2009. And the graph itself in purple is autism rates. And in pink here is the organic food sales rates. So you'll see they seem to be increasing pretty much at the same rate. So the question would be, does it seem like autism is causing organic food sales, or is organic food sales rates causing autism rates? Can we really conclude that autism rates are increasing because of organic food sales, or vice versa? Here's another one. Can we conclude that ice cream rate consumption is causing an increase and decrease in the murder rate? So along the horizontal axis, we have the months of the year spanning from January to December. In red is ice cream rate consumption, and in green is the murder rate. And it turns out, as the months go by, the ice cream rate consumption and the murder rate consumption seem to be pretty tied closely together. You could be given the ice cream rate consumption and use that information to get a good understanding of the murder rate at that time. So does that mean that ice cream rate consumption is causing the murder rate? And one last funny one here. Along the horizontal, we have the years from 1999 up to 2009, and then we have these two graphs. In black is the films that Nicolas Cage was appearing in, like how many films he was appearing in during that year, and in red is the number of people who drowned by falling into a pool. And you see, again, they seem to be closely tied. So is Nicolas Cage movie appearances causing people to drown in pools? So, of course, the answer to all of the questions above is no. The input variables, one variable here, is not causing the changes in the other variable. One thing is not causing the other. What we're seeing here is correlation, association. It appears that you could actually use one piece of information to maybe make good predictions about the other variable. They're correlated, they're associated. You do seem to see a pattern, but that doesn't mean one is causing the other. Here is one last graph where the answer is actually different. Along the horizontal axis, we have years from 1900 to 2009. In black is the cigarette consumption rate per capita. It's increasing up till about the mid-60s, early 70s, and then it starts decreasing. And you see a couple decades after that, the lung cancer death rate. It seems to follow the same pattern. This one in blue is for males, and the one for red is in females. Now, you see that there seems to be this correlation, this association between cigarette consumption and lung cancer death rate. And in all the previous graphs, I said, no, it doesn't make any sense to say one's causing the other. But as you know, nowadays, we really can say that cigarette consumption is causing lung cancer. So if you smoke more, it causes you to have more likelihood to die from lung cancer. So can we really say that cigarette consumption causes lung cancer? Turns out the answer to that one is actually yes. So what's the difference? What's the difference between the first 4 silly graph examples I gave you and this one? And how can we, out in the world, take these sorts of associations and correlations between variables and distinguish between simple correlation and actual causation? How can we do that? So how can we tell the difference? It reads, we need to have a clear understanding between the difference between causation and correlation. This is an extremely common area of confusion for people, and it's quite common to see people make false conclusions about causation when all we can really prove is correlation. Example, sometimes 2 things are associated, they're correlated, but one of them is not causing the other. So, for example, it turns out the murder rate increases as the temperature gets higher. That is just a fact. You can look at that around the country. As the temperature gets higher, the murder rate goes up, and as the temperature decreases, the murder rate goes down. It also turns out that people tend to eat more ice cream as the temperature increases, and they eat less ice cream as the temperature decreases. So the murder rate and the consumption of ice cream happen to be rising and falling at a similar rate, but one is not causing the other. So having a correlation between 2 variables means it's possible that there's a causal relationship, but you would have to prove that causation, and you cannot just assume it exists because you have correlation. It turns out temperature is causing the increase in ice cream consumption, and it turns out temperature is causing that increase in the murder rate in those warmer months. We have a lot of evidence for the causal relationship between temperature and murder rate, and a lot of evidence for the causal relationship between temperature and ice cream consumption. What we're actually saying here, it's called a confounding variable. Temperature is what's called a confounding variable, and we're going to look at that in the next video. As another example, sometimes 2 things are associated and correlated, and there is actually causation. So it turns out that smoking does actually increase a person's likelihood of getting lung cancer. And of course, for many years, this was unproven. The tobacco companies fought hard against that idea. So the tobacco companies were making a claim that people had a certain gene that made them more likely to become smokers, and also that gene made them more likely to develop lung cancer. What they were really saying is that this hidden gene was acting like a confounding variable that nobody knew about. They said this gene was acting like the temperature in the previous example, that the gene was making them more likely to develop cancer, and the gene was making them more likely to become smokers. And that's what was causing the correlation, that it wasn't the smoking causing the cancer, it was this gene. So how do we prove that it's actually smoking that's doing it and not some hidden gene that couldn't be discovered yet? So watch the next video and we'll get into the details of how we figure that out.